is going to double as a tutorial on how to use Packet Tracer for Cisco Academy affiliates, as well as how to do troubleshooting. Our goal is simple. Check this out. All we want is for this PC right here to be able to do an FTP, log into this FTP server right here. The networks are really simple. This segment of the network right here is the 10.1 network. Over here we have the 10.2, and then we have the 10.3 for this leg of our network right here, and we should have a 24-bit mask across the board. So we're doing some custom subnetting. So what we want to do is have this PC be able to go to the server. So what we're going to start with is verify that we can ping that server to begin with. So we'll bring up the PC. This is what I would do. I'd say I want to ping to 10.3.0.5, and that is, by the way, the IP address of this server. If we hover over the server, it'll tell us that the IP address is 10.3.0.5, and this PC's IP address is, if I click here, is 10.1.0.5. So we want to try the ping from here down to the server. And we're getting a message saying destination host unreachable. Now that's good news. That's somebody on the network telling us, hey, I don't know how to get there, a router. I killed your packet. I would love to forward it, but I don't know how to get there. So let's take a look at the default gateway. ipconfig on this device shows that our default gateway is 10.1.0.1. I would assume that I can reach this device because it's the guy who told me I can't reach your packet. So let's just ping him to be sure. 10.1.0.1. And sure enough, we can ping from here to our default gateway. So we know this leg of our journey is okay. Let's go to R1. So on R1, we could go ask him what's going on, and we could say, can you ping over to 10.3.0.5? Again, that's the IP address of this server right here, and that is timing out. Now, why can't it get there? Well, let's take a look at the routing table on this. We'll do a Control-Shift-6 to break that and do a show IP route. So what, this is not good news for R1. R1 says that he is connected to the 10.1.0 network, which is right here, but this interface is not up and active. There's no route for the 10.2 network right here. This red indicator inside of Packet Tracer is also indicating that we have a failure. So maybe the interface is shut down. That's a good possibility. So let's go to R1 and check that out. Show IP interface brief. And look at this. Interface FA01 shows up, down. It doesn't say administratively down. So it's not shut down manually. It's not up, though, at layer 2. So layer 1 physical, we're connected to. That might or might not mean we have a cable attached. But up, down certainly means that layer 2 is not happy. So what could be causing that? Well, let's take a look at the interface. And here's interface FA01 right here. And it looks pretty straightforward. We have an IP address. We have IPNet outside on that interface. That's good to be aware of. And on FA00, we have IPNet inside there, so we might have to tackle that later. But I don't see anything funny here that would indicate why that interface is down. So when we're troubleshooting, we want to remember the Osi Reference Model and troubleshoot from the ground up. If we don't have connectivity from R1 to R2, we might want to physically inspect and verify we have a cable, or more importantly, the right cable. Check this out. This solid line represents a copper straight through cable. That's what that does. Now, that's the perfect cable from a switch to a PC, or a hub to a PC, or a switch to a router, or a hub to a router. But if we have two like devices, like two routers, back to back, they're both sending on pins 1 and 2 with fast Ethernet. And as a result, they're not able to hear each other because they're both trying to send on the same signals and the other side isn't trying to listen. So we need a crossover cable to get the send pins from one side to the receive pins on the other. So we need to remove the cable. I'll get my little X tool. We'll take out this straight through cable and we're going to put in a copper crossover cable. So I'll click on copper crossover and connect to the available port and the available port. And that looks much happier. So any like devices, we need a crossover cable. Why? Because the send and receive pins need to be wired to each other. A hub or a switch is expecting to receive on pins 1 and 2, while a router is expecting to send and receive on pins 1 and 2, not receive. So the crossover cable simply fools both sides and makes the send pairs on one side show up at the receive pairs of the other. So now that that's in place, let's verify our connections. On R1, show IP route. And, well, at least we have our directly connected network now. So R1 says, if we do a show IP interface brief, R1 is saying that we've got 10.1, which is up and up. That's off of FA00. And 10.2.0.1 is up and up, and that's here. So let's just verify we can ping our neighbor R2. Now, for convenience sake, the last octet I just named the same as the router. So R2's addresses all end in 2. So if we try to ping 10.2.0.2, which is R2's address, we might lose 1 for the ARP, and there we go. So we have great layer 1, 2, and 3 connectivity. Icmp is a layer 4 protocol that we use to verify layer 3 connectivity. So ping works from here. So maybe I could do a ping from PC1 all the way to R2, and that would verify my conversation so far. So let's try a ping from PC1 to this IP address. In fact, I'll copy it, 10.2.0.2. So we'll copy that, go back to the PC, do a ping, and then we'll paste in that answer. Okay, so a ping from here to 10.2.0.2. Now that is not working. Now we realize that Nat is doing some translation here on R1. Perhaps the Nat isn't working correctly. Let's go investigate. So on R1, well, this is exactly how we'd go. Identify the fault domain, identify what is working, and then find where it's not working and tear that apart and look at it. So if we do a show run, here's our NAT pieces. On R1, FA01 is the outside interface right here because of that command. And that's the only reason it's the outside interface, is because we configured it that way, or somebody did. And then FA00 is IPNet inside. If we go down further in the config, we can see the Nat Pools. So here we have a Nat Pool called Pool 1, which is going to network address translate people into the pool of 23001 through 30 with, it looks like, a 27-bit mask. So we're doing some custom subnetting on that as well. So that's perfect, by the way. So those 3 bits from the last octet would equal the valid IP address ranges of 1 through 30. So it happens to be that part looks pretty good. And then we said IPNAT inside source list 1, meaning anybody who matches access list 1 is allowed to be translated into this pool called Pool 1. And access list 1 says anybody who's sourcing their traffic from the 10.1.0 network based on the wildcard mask. So that part looks good. I was expecting a problem there, but the NAT looks okay. I don't see any problems with that. We can ask R1 about that with the show IPNAT translations and see what he has. He doesn't have anything at the moment. Maybe they timed out. Let's do a ping again. And let's go back and ask R1 if he has any translations currently in the pipe. And check that out. This is measurable proof that R1 is doing the translation. So he's taking the PC's IP address of 10.1.0.5 and translating into 23.0.0.1, and that's perfect. That's the first IP address in that pool. So NAT's working. What else is going on? Well, if the packet makes it to the router and the router does NAT and the router forwards it, and we know that R1 knows how to get to this IP address because it pinged it earlier, perhaps R2 can't get back to the 23.0.0.1 address. That's a possibility. Let's ask R2 if he knows how to reach the 23 network. So we'll go to R2 and just ask him. Show IP route says that this router doesn't know how to get to anything except for directly connected networks. 10.2, which is this network segment right here, and 10.3 is the only 2 networks, and it certainly doesn't know how to get to the 23 network or even the 10.1 network for that matter. So our routing protocols seem like they're not working. Let's see what routing protocols we have. So on R2, we'll do a show IP protocols, and that will show us what routing protocols that we have. It says we're running OSPF 1. It states that we're routing for 10 anything. So that means that R2 is, willing to be doing OSPF on these 2 interfaces because they both start with 10 something. Let's see if he has any neighbors. Show IP OSPF neighbors. No neighbors. Here's what should happen. R2 and R1 should become OSPF neighbors. Remember all the rules. Well, maybe in your studies you haven't got to this yet, but with OSPF, we have to have certain agreements in place. It's like being a member of a homeowners association. Everybody on the block has to play by certain rules or you get kicked out, or at least a fine. with OSPF, we have to have several things in place. The flags all have to be matched up. For example, a stub area or not so stub area flags and so forth. We also have to have the same OSPF area. So maybe this guy thinks it's area 0, maybe R1 thinks it's area 1. Also, we have to have the same networks in place. So here, let's take a look at R2, and we'll do a show run. And let's just take a look at the interface. FA00 is 10.2.0.2 with a 3-octet mask. So R2 believes this is the 10.2.0 network right here. Let's see what R1 thinks. If we take a look at R1 and take a look at its interface FA01 right here, it thinks that it's, the 10.2.0. Oh, check it out. The mask is wrong. Now, they can still communicate because they both, from an IP perspective, they can talk to each other, but OSPF is more picky. OSPF says that if this router believes it's a 24-bit network and this router believes it's a 16-bit network, they won't become OSPF neighbors. So we need to fix that. So we'll go into interface configuration mode for FA0/1. I'll put my mouse right on it. That's where we're configuring right now. And I'll simply change the IP address for a 24-bit mask. So it's going to be 10.2.0.1 with a 3-octet mask. Now OSPF, once that happens, we're going to have some hellos that go back and forth, and wow, that was really, really quick. So the neighborship came up, and now we have a neighborship between R1 and R2. Again, it's pieces, little teeny pieces, bit by bit, identifying the fault domains. So far, what have we had? We had a bad cable. That was layer 1 of the Osi Reference Model. We had a bad OSPF neighborship, so they weren't forming a neighborship, but now they are. Let's take a look at R2 and show IP OSPF neighbors. So sure enough, we have a neighborship between R2 and R1. And let's take a look at the routes. Okay, and so here R2 knows about the 10.3 network right here. R2 is directly connected to the 10.2 network right here, and we have dynamically learned through OSPF the 10.1 network, which is right over here. So let's try our ping again from the PC out to 10.2.0.2. Now it's still not working. Why? Now this is a little bit tricky, but if we follow the bouncing ball across the path, remember that we're doing network address translation on R1. So if we look at the IP NAT translations, this PC is being translated into the source IP address of 23.0.0.1. When that packet goes to R2, which is the destination in this case, R2 is asking itself, do I know how to return the Icmp echo reply back to the 23.0.0.1? And the answer is no. I don't have a route for it. It doesn't have. Now we could solve this by doing a default route on R2 that says send everything to R1, or check this out, we could have R1 advertise the default route that would then tell R2 to send everything, or we could create a static route on R2 that says to get back to that 23.0.0.1 range, go ahead and send it to R1, or lots of options. We could create a static route on R1 that says I know how to get to the 23 network and then redistribute that into OSPF. In the real world, that would be our preferable treatment, because in the real world, we're going to have more routers than just this guy. And default routes are not to be played lightly with in the real world either. Just saying, hey, yeah, send everything my way, because you probably don't want everything, the entire internet, for example, sent your way. So what we'll do is this. On R1, we're going to create a static route for that range of addresses in the pool. So if we go up to the config, which I'll show you again, show IP or show run. Packet Tracer doesn't have all the shortcuts as the iOS does, but it's got a really big set of tools. It's fantastic. So we want to create a route to the 23.0.0.1 through 23.0.0.30 with that mask. So what that would equate to is the 23.0.0.0 network with a 27-bit mask. If we create a static route for that, and then we point that to null 0, which is the bit bucket, we can then advertise that route out to all our buddies via OSPF. So what's going to happen is R2, if he has a packet for the 23 network, he's going to forward it over to R1, and R1's going to have a static route for that, but it's also going to have a more detailed route for the NAT translation that it just created for PC1. So R1 will take it and forward it. That may be a little bit advanced, but you know what? It's good to see how it works. So let's go ahead and do the static route. IP route, spelled correctly, Keith, going to, and let's see, that range is going to be 23.0.0.0. That's a 27-bit mask right there. And I need to say that's going to go to null 0, which is the bit bucket. So right now we have this 27-bit route that says I send it to the bit bucket. Now, fortunately, if we're doing network address translations for people, we're going to have their 32-bit IP address, and we know exactly how to reach them. So let's do this. Let's add that route to OSPF. So show IP protocols is going to show us what OSPF process we're running, which is OSPF 1. I'm going to say redistribute static. Now that says any static routes that I have, go ahead and put into OSPF. So what's going to happen is R1 is going to take the static route for the 23 network, put it into OSPF, and now it's going to advertise that specific route via OSPF to R2. So R2 should have, if it all went well, R2 should have a external OSPF route right here that it learned from 10.2.0.1 regarding the 23.0.0.0/27 network, which is perfect. Now, could we have done this with a /16 or /24-bit mask? Yes, it would have worked the same, but this is nice and tidy just for that pool of addresses that we're natting for. So now that that's done, let's see if PC1 can go ahead and successfully ping R2. And it can. So we've had a couple challenges so far, but we're almost done. So the PC has been natted at R1. That netted address pinging R2, R2 replies, but our goal was for this PC to talk to this FTP server. So let's see if we can do the whole run here. So we're going to do a ping to 10.3.0.5. That is the server, and that is not working. Okay, so we're almost home. Let's go take a look at the server. And here in Packet Tracer, which is a really great tool for Cisco Academy affiliates, let's go ahead and take a look at the desktop, go to the command prompt on the server, and do an IP config. It's 10.3.0.5, and its default gateway is right there, and that is wrong. The default gateway should be 10.3.0.2. This interface right here of R2 should be our next hop. So we'll need to fix that. So we'll go to Fast Ethernet, and we'll go to the global settings, and the default gateway should be 2. So once we've made that change, we can close this window. Actually, we'll go back to it, and we'll test with the ping. So let's go to the desktop, command prompt, and let's do a ping of 10.3. Actually, let's do this command again. Make sure it took. And we'll do a ping to 10.3.0.2. Okay, that works. So now the server has the correct default gateway. Finally, let's go back to the PC and see if the PC can actually get there. 10.3.0.5. Wow, full connectivity. Life is good. One last piece. Can we open up an FTP session to it? So we'll do FTP to 10.3.0.5. And it's trying and it's trying. Now, here's the kicker. We know that we have connectivity from a routing perspective. So what could stop an FTP session from working? Well, it could be an access list stopping the TCP FTP well-known port of 21 anywhere on these routers. That could be the case. Or it could be the server itself that is simply not running FTP. So let's take a look at the server. And under the config, under FTP services, we probably should enable it. So we're going to enable FTP on that server. And now that it's enabled, let's go back to the PC and try it again. And there's our prompt. The username and password is Cisco by default, and we have FTP successfully in the bag. In this troubleshooting lab, we highlighted the features of Cisco's Packet Tracer for the Network Academy, which is a fantastic tool. And we've also troubleshot OSPF with adjacencies, physical issues with the wrong type of cable between two like devices. We had the FTP server with a wrong default gateway. We also had a situation where the network didn't know how to reach the 23 network address. and that was the pool of addresses that we were using for a network address translation. I've enjoyed walking you through this troubleshooting tutorial. I hope you had fun, and I look forward to seeing you in another video. Have a great day.